Tonight, our event is Journey to the Center of the Milky Way with one of my favorite speakers, Professor Cornelia Lang from the Department of Physics and Astronomy, and she is I had to write it down, a professor of astronomy and astrophysics at the University of Iowa.
Astrology. Sometimes that happens.
No, that's why I looked it up. I wanted to make sure I got it right. And I'm going to let her tell you about all her experience with space and the Milky Way and all that, because it's so far over my head. I just sit in awe. Yeah. Oh, boo. Okay.
But stay tuned, because there's a couple of quiz questions, Beth.
Uh-oh.
So,
okay.
All right.
So have at it.
Okay, great. Well, thanks so much for coming out on this evening. And, oh, that's fantastic. That's great for the lights. So I'm going to tell you, I'm going to give a very general talk about the kinds of things that I think about in my work here as a professor at the University of Iowa. And I can't start a talk like this without showing just a few snapshots of the wonderful students that we have in the Department of Physics and Astronomy. We have one of our graduate students here tonight, Aaron. He's not allowed to answer the quiz questions, okay? And so in the top panel up here, I show some undergraduates as well as my graduate student, Dylan, who's also down here. And here we are at Film Scene doing an outreach event. Our signature is these tie-dye lab coats. I know that folks come over from our department to do programs for the library all the time. And I currently have 3 students that I'm working with almost daily. I have a graduate student, Dylan, who just got his master's degree, and he will be continuing on to do a PhD with me. He's actually away right now, but he comes back next week, and then he will be going to Australia to spend 4 months working on a data set we have there. And I'll talk a little bit in my talk tonight about why, for the center of the Milky Way, we need to observe from the southern hemisphere. It's much better viewing of the center of the Milky Way. And then I have 2 undergraduates, Gina Crom right here, and she is from Western Iowa, and she is working with me here on campus this summer. We meet every afternoon. And then Haley Moore is these 2 are rising seniors, and Haley's from Cedar Rapids, and she is spending the summer at the University of Maryland on a fellowship working on climate science this summer. So she's broadening her horizons a little bit. So a lot of the work that you see when we get to the part of the slides that are from my research, a lot of that work is due to the students that you see here. So that's a feature of our department, and I thought I would open with this very fun slide. Last time I spoke at the library last month, I talked about the long tradition we have in our department of getting undergraduates involved in research, and I am going to start tonight by just showing the little video clip telling that story before I talk about my research. But this is a fantastic image that many of you are familiar with. James Van Allen, Wernher von Braun, and Dr. Pickering holding up the Explorer 1 spacecraft. The instrument that's in the nose cone here was designed and built at the University of Iowa. And 3 students, 2 physics students and an engineering student, got a chance to participate in a rocket school last October, and they simulated this historic image. And this is definitely, I hope, the way that the future looks in our field. So, as people are still coming in, and before I get into the center of the Milky Way, I thought I'd just show this to give you a sense of what our department is like and the way that we work with students, which goes way back to the time of Van Allen. So this should start. We tried it a minute ago. Let's see. It's right over here. Let's just go to this one.
Professor James Van Allen is really known as the father of scientific space exploration.
Between 1951, when Professor Van Allen arrived, and 1975, University of Iowa was the place where spacecraft instrumentation, design, construction, tracking occurred. It was the place in the world.
And the University of Iowa has maintained a very strong leadership role in space exploration.
My research focuses on the very core of the Milky Way Galaxy. When you look out in the universe, especially at very, very far distances, you are primarily seeing the centers of galaxies. And so if we can understand our own galactic center, we can only hope it will inform us about these more distant systems that populate the universe.
I study the sun and how the energy from the sun flows through the solar system and impacts both the evolution of the solar system and the Earth. The one object in our solar system, and admittedly a very important one that we've never visited, is the sun. So currently, researchers here at the University of Iowa, as well as a team of scientists and engineers across our nation, are working on this billion-dollar mission, Solar Probe Plus, to send a probe to the sun to actually sample the outer edges of the sun's atmosphere, what's called the solar corona.
The trademark of James Van Allen, any story that you hear from his early days includes undergraduates knocking on his door saying, I want to work on the space program with you, and him saying, please join. That has remained a hallmark of our department, involving students, undergraduates and graduate students, even from other departments, in the exploration that we're doing.
The first time I came into this lab, I was just overwhelmed. It was, what's this, what's that? Gradually over time, I learned what each and every single piece of this lab does.
I'm looking at galaxy clusters and the interactions that they partake in. I wanted to help out with this, and that's exactly what I'm doing now as a freshman at the university.
Every day I come in and they teach me something new. It's amazing. It's one of the greatest feelings in the world.
The Solar Probe Plus mission will launch in the summer of 2018. So it's just a few years away. It's a really exciting time right now in space physics and here at the University of Iowa.
All right. So what I want to tell you guys about tonight is the work that I'm doing with my students. And so what I'd like to do is start very much at the beginning, okay? So what is a galaxy? If we're going to talk about the centers of galaxies, we better first talk about what a galaxy is to start, okay? So the way that astronomers define a galaxy is that it is a collection of anywhere between 100 and 300 or 400 billion stars, okay? And astronomers don't get very bent out of shape about the exact number, okay? So what we like to say is, what's a factor of 2 among friends, okay? So if you take an exam in my class, you will get a correct answer if you put 100, 200, 300, or 400 billion stars in a galaxy. You will not get a correct answer if you put 1 million, and you will not get a correct answer if you put 1 trillion, but anywhere in the hundreds of billions, you're good, okay? Now that's not true in most sciences. But stars are not the only things that make up galaxies. When we look at galaxies, especially in the optical part of the spectrum, and we'll talk about the whole spectrum in a minute, we primarily see stars. So when you look at these beautiful galaxies, you often see stars. You often see cloudy stuff that actually is just literally so many stars together you can't disentangle them from each other. But there are other components as galaxies as in galaxies as well. Stars make up the majority of the mass of a galaxy, but hot on the tail of that mass in stars is the mass in interstellar gas. And that gas is primarily hydrogen with a little bit of helium mixed in. And then we have all the other elements. So if you ask an astronomer to map the periodic table, there's some funny cartoons of this online. It's basically hydrogen and helium. All the other stuff is kind of, we're not that interested in that. So a chemist's periodic table looks very different than an astronomer's. And then we also have a very important component of the interstellar medium, which is dust. And when I say dust, I actually mean dust. So I mean tiny particles that are primarily carbon, and they can range anywhere from microscopic grains that we would consider even smaller than visible dust, all the way to things that are the size of minivans. Those are also considered dust in the interstellar medium, okay? And these dust particles tend to be built into the clouds. And it's actually the dust that causes darkness in many parts of the sky. So for instance, right here, what you're looking at is the shadow. You're looking at dust mixed with gas that forms this disk that most spiral galaxies have. And so what you're looking at here is not a lack of light, and you're not looking deeper into the galaxy, you're actually looking at the shadow of material that has a large concentration of dust. And we'll see this again and again in tonight's talk. So this is what a galaxy is. This is my favorite galaxy, NGC 2997, its phone number, as we like to say. And it's located in the southern part of the sky, so it's a difficult galaxy to see from 41 degrees latitude north, which is where we sit on our planet. You have to go to the southern sky. This is a face-on view of a galaxy, and this is an edge-on view. And then some galaxies are tilted partway in between, okay? And so what you're looking at here is this galaxy is sort of tilted halfway from face-on to edge-on. And so one of the things when you study galaxies as an astronomer is you often have to calculate the inclination angle, because if you're going to derive physical properties from your images of galaxies, which is something we do, you have to know about that inclination so you might make the right calculation. So that's what a galaxy is. Now, in our galaxy, we're interested in I'm interested in studying the very center of the Milky Way, okay? But to observe the center of the Milky Way, I have to figure out which direction to look in, okay? So this is your first quiz question. Where is the sun in our Milky Way galaxy? And this is a little artist's conception of the Milky Way. You actually saw it in the video as well. It's one of the best representations of our galaxy that scientists have put together. So it's a model of our galaxy. It's a sketch, but it's based on lots and lots of observations. It's very difficult, as you know, to study the shape of our galaxy because we live in it. So it's like trying to study your whole body if you were a single heart cell or something. And so to try to get a picture of what the galaxy looks like, you really have to study a lot of other galaxies and do a lot of modeling. Okay, so this is 150,000 light years across, and you've got a couple of choices about where our sun lives, okay? The first one is, does our sun live at the edge of the Milky Way? All right. Come on in. We're doing a quiz. So we're wondering where the sun is in our Milky Way, okay? So this is your first choice. How many people think that the sun is way out on the edge of the Milky Way? Okay, no takers, that's fine. What about, second choice would be right at the center? Not possible. Okay, great. So I think most of you would vote for somewhere about halfway out. All right? What? So the sun is actually located at a distance of about 25,000 light years. It's going to depend on how you're orienting your view of the Milky Way, okay? But we know what arm, we have named, astronomers have named the different arms of the Milky Way, and so we've mapped out where we think the sun sits in our galaxy. And so we're about 25,000 light years away. Astronomers also have this other unit called a parsec. So the galactic center is about 8,000 parsecs. A parsec is just about 3¼ light years. It's an angular measurement. But that's where the sun sits. So we liken the sun to living in the suburbs, okay? And we liken the center of the galaxy to being a very, very active downtown region. And so one of the reasons you might want to study the very active downtown region is one of the reasons, like you like to go to New York City or you like to go to downtown LA. You like to see a region where there's many more interactions, the physical conditions are more extreme, there's more traffic, there's more things to purchase, you know, there's just a lot going on. It's very good for us that the sun lives at the edge of our galaxy, okay? Because in order for a star to harbor a planet that can form life, we want to have a nice, quiet, suburban existence, okay? It's very hard for the kinds of stars that might harbor planets to have a quiet, life-bearing environment in the galactic center, okay? The other reason you might want to study the center of a galaxy is to learn about, as we said in the video, about what other galaxies have at their centers, because most galaxies are so far away, we're never going to get a clear view of what's happening in their central region. But 25,000 light years, that's not too far away. And so we can actually study the things in detail here and then try to understand what might be going on in other galaxies. And so some of the images you're going to see tonight are very, very sharp pictures of what we know is happening at the center of our Milky Way, okay? So what usually exists at the centers of galaxies, okay? Just like we know in big cities and downtown areas of large metropolitan areas, we usually have skyscrapers, we usually have hot dog stands, we usually have long taxi or Uber queues, right? Same thing is true here. Most galaxy cores either have a supermassive black hole, and we'll talk about that in a minute, or a very intense burst of stars forming, or both at the same time. So these are things that don't often happen in the other parts of galaxies. So this, of course, is a sketch, but this is what a supermassive black hole and the material falling into it looks like, okay? And so what you see is you see a disk of material, and you'd never be able to resolve this with a telescope. This is a conception of what's happening very close to the black hole. You also see a disk of material. And you might ask me, well, I thought black holes were black. How can you see them? And the answer is you're not seeing the black hole itself. The black hole is, I mean, you can see a little black thing right there. What you're seeing is material that is being heated to such high temperatures that it's giving off light at different wavelengths, okay? Due to conservation of angular momentum, you build up enough rotational energy that has to be released, and it's often released in the form of a collimated stream of particles that have a strong magnetic field associated with them. And they're these beautiful jet-like features. And both disks and jets are not just theoretical things, they've actually been observed. So in the case of M87, which is a very famous galaxy now, we'll come down to a picture of the black hole in a minute. In M87, you can actually see, this is a Hubble Space Telescope image, you can actually see this narrow collimated jet. And this jet extends over 5,000 light years. So that's a sizable fraction of the galaxy. And this galaxy is 60 million light years from us. And Hubble has such sharp imaging that we're able to see this jet that tells us there's a very extreme black hole in its center. Did you have a question, sir? Yeah.
So pretty much if you go anywhere near there, anywhere past there is not safe for humans.
That's true. And at the end of my presentation, if you stay awake long enough, I am going to show you a little cartoon of what happens if I get thrown into a black hole, which is what a lot of my students at the university would like to see by the end of the semester. Well, we'll find out, okay? That sounds like a good prediction that you have, okay? This is an image of so M87 is a relatively nearby galaxy. M82 is a closer galaxy, near and dear to a lot of our hearts. It's a gorgeous thing, and it's only 13 million light years away. It has an intense starburst at its core. So it doesn't have the supermassive black hole, but it has the new generations of stars just booming and putting energy into the interstellar medium, and you can see evidence of that. So this is an optical picture, and you can see the dust. So all these dark patches are regions where you have material that has a lot of dust content in it. And that signals to astronomers, that's a signal of a place where new stars can be born. Because stars form in clouds that have clumpy, cold, dusty cores. That's where new stars are born. And so this tells me, as an astronomer, there's a lot of potential for star formation. And there's also a generation of stars that caused the gas to glow bright red. This is H alpha, which is a common line that we study in the optical part of the spectrum. And it's mainly produced by starlight heating up surrounding material. And so we can see on even galactic-sized scales that this galaxy is very much impacted by the star formation in its core, okay? And so we want to know, how does this actually happen? So we see evidence that this is happening, but what's happening on small scales to lead to these big features? What's even more amazing is that these features can extend beyond the size of the galaxy, even into the intergalactic medium. So again, we're revisiting our friend M87, and now we're looking on a size scale that's, almost as big as the galaxy itself, 65,000 light years. The core of the galaxy is down here. That image I showed is all here, and this is a larger jet feature that lines up with the other one, and it's just pumping relativistic particles over large scales into the interstellar medium, and you can even see the particles traveling around. So this galaxy's core has an impact not only on the galaxy itself, but even the surroundings. And again, you can see M82 with a more sensitive imaging. You can see that those plumes actually, we were just scratching the surface in that previous image. If you look at a more sensitive image, you can see much larger plumes, again, from that starburst activity. And then finally, this is an image from the Hubble Space Telescope, and you can hardly see it here. But if you zoom into one tiny dot that's very faint, you blow it up, you can actually see a red glow from a galaxy that is as close to the edge of the observable universe as we know. This is a very highly redshifted galaxy. And what you're seeing is light from presumably a starburst that has been redshifted into the red part of the spectrum, and you're seeing the center of that galaxy, even though that galaxy is at the edge of the visible universe. So understanding the cores of galaxies is really a very fundamental thing to our understanding of the whole universe. And so the central question here is, how can we better understand the centers of galaxies? And I think one of the answers is by first looking at our own and trying to learn some lessons on the way out. Sir?
So all of these stars that are visible now, were they impacted by like red giants or things like that?
The stars that are currently visible, were they impacted by red giants?
Yeah.
Many of the stars that are currently visible, like our sun, will become red giants, okay?
And they all suck up every other anything close to it.
Red giants are very, very bloated stars, so they're not doing any curvature of space and time. But we'll talk at the end a little bit about your question, okay?
This is just a lot of stuff that I've seen in school.
Yeah, exactly. Yeah. Well, good. Well, I think we're going to talk about young and old stars in a few minutes. So there's two ways to learn about what's going on. So one, of course, is by studying our own galactic center. And then the other one is by looking in a lot of detail. So many of you know that in April of this year, the very core of M87 had an image made of the shadow of the black hole. And this is an unbelievable contribution, unbelievable discovery. This is a simulation. We are now looking at something called the event horizon, which is the edge of a black hole. Past that edge, no light can escape. And so that's why the center of this simulation is completely dark, okay? We're looking at a distance of 7 Schwarzschild radii, which is a measurement we use to try to categorize where that event horizon would be. And so in this galaxy, this is all the material that's soon to be falling across the event horizon, information about which will be forever lost. But because our telescopes are sharp enough, we can actually see the shadow. We can actually image the shadow against the bright stuff that's falling in. So this is the simulation. And using a series of telescopes, different parts of the planet, combining the signals from those telescopes at very, very high angular resolution. That technique was actually partly pioneered here at the University of Iowa. We didn't contribute to this image, but about 30 years ago, our scientists, using an antenna out by the Coralville Reservoir that some of you guys have seen, were a pioneering part of the technique that was used to make this image. So many things in space have a local connection if you probe far enough. So this was the Event Horizon Telescope actual data showing this was what was predicted and this is what was actually seen. And so we can talk more about this at the end. But that's, of course, the way to actually know what's going on in the center of a galaxy. And that's only going to be available for a few nearby systems where we can make these measurements. But really understanding the center of our galaxy is one of the things that will help you understand the centers of most galaxies. Now, this poses challenges for us because in order to study the center of our Milky Way, we've got to look through 25,000 light years of junk or of dust and gas, okay? And so that makes it a very, very dark region of the sky. So many of you have probably seen, how many of you have seen a dark view of the Milky Way from a really, really dark spot, where you can actually see these dust channels, okay? So what's amazing, and I'm still mind-boggled by this sometimes, is when you're able to see such a dark sky, your brain automatically assumes that in these dark channels, you're looking deeper into space, right? It feels like that. What you have to remember is that these dark channels are actually like dark curtains coming down and preventing you from seeing what's behind, okay? So for instance, in this part of the galaxy, we are looking through the most interstellar material, and so it's a very, very dark part of the sky, visually. At other wavelengths, it's incredibly bright. But this is where the center of the galaxy is. So if any of you are familiar with the constellation Sagittarius, it's either a lovely teapot or a archer. Sagittarius points right to the center of the galaxy. But the problem with the center of the galaxy is visibly it's dark. So we can't use any of the telescopes that you're familiar with to study the center of the galaxy. You can't use the telescope on Van Allen Hall. You can't use Hubble. There's one camera on Hubble you can use. You can't use Kitt Peak. You can't use the telescopes in Hawaii. Most of the telescopes that you're familiar with work at optical light. And we in the galactic center community have to use the infrared, the X-ray, the mid-infrared, and the radio to study the galactic center, okay? Second quiz question. Which one of these are all of the tools in our astronomy toolbox. Which one of these has the longest wavelength? Do you want to take a guess?
Yep. Gamma rays.
Gamma rays. So that has the longest wavelength. Okay. Does anyone disagree? So gamma rays have the shortest. Okay. They have the highest frequency. But the other end of the spectrum is?
Radio waves.
Radio waves. Okay. I know. Gamma rays are radio waves. Next question. Which one of these carries the most energy? Gamma rays again. So there's I know, there's an anti-correlation. The shorter the wavelength, the more energy the light carries, okay? Now this is a last question just for you.
The longer
yeah.
the wavelength, the less energy.
The lower the energy. So radio waves don't actually carry too much energy, although there's some, as with everything, there's a couple of times when the rules are broken. But this question is a special question for you. All of these forms of light, which one travels the fastest in space?
Ultraviolet. Oh, what is it? Let me think.
It's a little bit of a trick question.
Microwaves.
Not, they all travel at the same speed. In space. In air or water, it would be different. But in space, which is essentially a vacuum, all of these travel at the speed of light, okay? And just to remind you, some of you probably saw this in maybe a high school or college astronomy class or physics class, but this is the full electromagnetic spectrum. So here's gamma rays up here. They have very short wavelengths, very high frequencies, and as you move down to radio waves, things get much longer, okay? And you can see that our eyes and most of the telescopes we're familiar with are pretty limited, okay? We're not particularly inclusive sometimes when it comes to all the different wavelengths we have access to. So astronomers often will introduce themselves and tell you either that they are attached to a particular object, like, oh, I'm a galactic astronomer, or I'm a planetary astronomer, or I'm an extragalactic astronomer like Alen, or they will say, I'm a radio astronomer, and I don't want to talk about things if you're going to talk about a visible telescope. And so astronomers are a little funny. They like to attach themselves to particular things. So one place they attach themselves to is this spectrum. The other thing is, if you think about it, there's a lot of different ways to collect light, and they're not all the same for all these forms of light. So these are just an example of how we essentially build these light buckets to collect these different forms of light. So here are some radio telescopes, and then here is an infrared telescope, an optical telescope, X-ray telescope, and they all have different techniques for how they can bend and focus the light so that you can make an astronomical image, okay? And that's a whole lecture in itself on how that works. But all these different forms of light have different techniques. So an astronomer, a really savvy astronomer, will try to get familiar with multiple techniques, but it does take time and it takes a lot of practice. Okay, so let's spend the next 15 or 20 minutes talking about the extreme astrophysics in the galactic center. So this is an image that I had a large part in making. This is just a stunning image. Every time I see it, I get excited again. It's made from 3 of NASA's great observatories, okay? And there's no visible light in this image, which is amazing to me, okay? So everything you see here is either a radio wave, an X-ray, or an infrared piece of light, okay? And so the yellow color here is from the Hubble Space Telescope, but it's from their infrared camera. The red light here is from the Spitzer Space Telescope, and both the yellow and red light are telling you about clouds that have been heated by stars that have dust inside them, and they're re-radiating that energy back into the interstellar medium. And so it's kind of like finding a fossil. When you study this yellow and red light, you are studying the remnant of what this cluster of stars has done to the surroundings. And so we use a lot of the same techniques as geologists. We backtrack, we measure things here, and then we backtrack and make calculations to what this cluster of stars must have been doing in its early days to create this. Okay, so this whole region of gas and dust has been heated by this beautiful stellar cluster here. Similarly, this is another stellar cluster here, and this is the footprint of how it has cast energy out into the interstellar medium and left foot and fingerprints of its energy. The yellow and, the white and blue light is the X-ray emission coming from this part of the galaxy. So we've got, and that comes partly from the material near the supermassive black hole, and then also some very interesting objects, clouds of gas, star clusters that have X-ray emission associated with them that we're still trying to understand this very hot and energetic component to the interstellar medium. So I'm going to, yeah, there's some beautiful structures here. This is called the sickle. This is called the arched filaments, and many of these things have different fun names. One of the things you get to do in astronomy is if you find something, you get to name it. So we've had fun naming things. So let me just give you some orientation. We are now looking very, very close to the center of the galaxy. The dynamical center of the galaxy is right at these crosshairs, and we're going to spend the last few minutes of the talk talking about that, because that is where the supermassive black hole lurks. But what you can see is that the supermassive black hole is not dominating the energetics of this region. This is a region that looks very much like stars have left an impact on this region. Our black hole is actually quite wimpy. So this is a region that's about 100 light years by about 30 light years. So we're going to talk about a couple of different parts of this region. And these are the questions that I am aiming to answer in my research. Those are in yellow. And then the white are questions that my colleagues are trying to answer. So these are the kinds of things we think about in the galactic center. So what causes the clouds that form stars to be more unusual in this part of the galaxy than in other parts of the galaxy? Are there new stars forming in this region? Can you form a new star cluster near a black hole? Is that possible? Is the Milky Way center strongly magnetized? So we know galaxies have magnetic fields. What happens at the centers of galaxies? How massive is the supermassive black hole in our galaxy's core? Can we make an image of the shadow of the black hole in our galaxy? I showed you the shadow in M87. Can we make one of our galaxy? And what happens if a star or a gas or a professor falls into the black hole? Okay, we'll get to that. You know what? I think I'm going to take some questions at the end, okay? Okay, real quick.
What I would say is, yeah, it is possible for a star to form near a black hole because there's enough potential energy.
That's a good point, and we will show some examples of that in a little bit, okay? Okay, potential. You use that word potential, very important word. The potential to form new stars, okay? So we know from our studies of the galactic center that there are some very impressive star clusters in this region. So I told you about the arched filaments. There's a beautiful star cluster called the Arches. There's the quintuplet cluster, which heats the sickle. And there's the central cluster of stars that surround the black hole. Yeah, so there's a lot of potential to form new stars. one of the places that we look for new stars to form are very dark places in the interstellar medium. So this is a cloud that is a very deep mixture of dust and gas, and we think it's on its way to forming a new generation of stars. And so we have done a study of this cloud. I've done this with my students. We call it the brick because you can't see through it, and it sort of has the shape of a brick. And we have found out some interesting physics. So one of the things we can do with our radio observations is we can study emission that many molecules make over different quantum mechanical transitions. So this is the ammonia molecule, the same chemical that you use to clean your house. And it lives in the interstellar medium, and when we compare how bright it is in these different transitions, we can get a measure of its actual temperature. And so we find that this cloud's temperature is about 100 Kelvin, which is pretty warm for forming stars. 100 Kelvin is like minus 200 degrees Fahrenheit. It's very, very cold from our perspective, but it's warmer than most clouds that form stars. And so we want to ask ourselves, how can this cloud that's a little bit warmer than usual form stars? So to ask that question, we first have to figure out what's happening in the cloud. We can also use certain transitions to study the motions of gas in this cloud. So these rainbow colors here show you streams of gas at different velocities. And we can tell from this beautiful pattern of blue to yellow to green to red to orange that this cloud is in the process of collapsing. It has some mixed emotions, right? And so we think that this cloud is in the process of collapsing to form a new stellar cluster. And so we have some evidence here that some of the clouds in this region can actually form new stars. One of the other things that we can study is, of course, the impact of these stars on the surrounding medium. So we zoom in here to the sickle region, and one of the images that my students and I have made is a very spectacular image showing in detail what the sickle looks like. And one of the things you can see right away is you can see the presence of stars that have aged. So these quintuplet cluster stars have been around for a few million years. And at that point, some of these stars get fairly unstable, and they start to lose material from the surfaces of the star. And you can actually pick up the wind of that star in the radio. So these little dots here are measurements of the stellar wind. Our sun has a stellar wind, but it has a very, very low density that it propagates into the interstellar medium. These stars have winds that are at least 1 million to 1 billion times more dense in terms of the particles that they push off into the surrounding medium. And these winds themselves can cause the whole edge of a cloud to glow. And so we can actually calculate from our radio observation, we can calculate the mass loss rate, and we can convert that into an energy of impact into the surrounding medium. So this tells us about how older stars have an influence on the surroundings. We also can see evidence of a very old star that has lost a bunch of its material and may likely turn into a supernova. So this is an unusual kind of star called a luminous blue variable star. And in order to stay stable, it has burped out, is literally thrown off about 10% of its mass. So the star itself is thought to be 100 times more massive than the sun, and the material in this shell is thought to be about 10 times the mass of the sun, and it's done this in order to remain a star. And stars do this at the very ends of their lives when they're very massive stars. And we can see a beautiful spherical remnant here in the radio. We also see evidence up at the top of this sickle for things that look like the pillars of creation. So this is another piece of evidence that leads us to believe that new stars might be forming at the tips of these pillars. And for reference, here's the famous pillars of creation from a nearby star-forming region, M16, that Hubble imaged. So we have a lot of evidence that we actually can form stars in this region. And we're interested in learning more about how that works. One of the other things that I study in my research is the role of the magnetic field. And this is just an absolutely spectacular image of the galactic center. This is now a bigger image. So we've been looking at this region mainly here. This is a little more expansive. And one of the most notable features, this is a radio image, are these beautiful filamentary strands. And these are thought to be tracing magnetic field lines. So these are synchrotron particles. These are particles that are very bright in the radio, that are charged. They're electrons, and they spiral around ambient magnetic field lines. So by studying these filaments, you can basically trace out the orientation of the magnetic field. This is the plane of the galaxy in this direction, and the fields seem to be largely perpendicular. And the reason why that's important is it tells us about how a galaxy may lose its energy out the top. Remember when we saw M82 had those large plumes of gas in two directions at an orientation that was vertical to the plane. So this is evidence in our galaxy that we would expect if our galaxy had a chimney of material, it would flow outwards in the same direction as these filaments. So understanding the magnetic field helps you understand how hot plasma gas gets directed out of a galactic core. And so I've been doing some follow-up observations with my students of these very, very thin magnetic fields. This is some new data that my student Dylan and I are still trying to understand how you get these striations, how is it connected to that sickle structure. There's a lot of things going on in the same place. Question? It's true, yeah. We think that particles are probably spiraling along these lines. Okay. Now, in the last few minutes here, I want to talk a little bit about the supermassive black hole because everybody loves studying black holes. I don't happen to work on the supermassive black hole, but I'm going to show you the work that a lot of my colleagues at different international institutes have put together. So people have long suspected that at the center of our galaxy we might have a black hole, but it's a very, very difficult measurement to make. And so one of the things you can do with a black hole is, since you can't see it, you have to infer or sense the presence of the black hole, okay? So this is a little funny cartoon where it's two scientists talking to each other, and one says it's black and it looks like a hole. I'd say it's a black hole. And so what you have to do in astronomy is you have to look for indications that there's something unusual going on that could be explained by a very large mass in a very small volume. So one of the things you can do is you can look for very unusually large motions of something like stars around a position where there's no light, all right? And for instance, you would never expect stars that are very, very distant to move across the sky in a matter of years, okay? And so if you were to see something like that, you may suspect that there's something causing that star to have that unusual velocity. And so that's exactly what scientists did. There are two groups. They're in tight and tough competition. The UCLA group, this is where I did my PhD. The astronomers at UCLA used the WM Keck Observatory. This observatory is located on top of Mauna Kea. Right now, as some of you have read in the news, there's a lot of upheaval at Mauna Kea because they're trying to put a very large new telescope on this property, which is a very special property for sacred site for indigenous people. So there's a conflict right now back and forth. Many of these telescopes were built after negotiations with the local indigenous folks in Hawaii. And so the controversy really is that the telescope they'd like to build is many, many times bigger than the ones that currently exist. But the Keck Observatory has been a very, very spectacular facility that the University of California schools have used. And then the competing group uses a site in Chile called the Very Large Telescope. Both of these groups make very, very high resolution pictures of the center of the galaxy in the infrared part of the spectrum, okay? So this field right here is just showing you a tiny, tiny region compared to all the images we've looked at so far tonight. Buried in the center of this image is the location of the center of our galaxy, and it's these stars that people have honed in to look at to see if there are large motions. And the work is absolutely spectacular. It has taken place over a 25-year period. It's now 2019. And the results are really spectacular. So let me try to explain it, and then I have a little little animation. So each one of these circles is an orbit of a star that's very, very close to the central black hole. Each data point represents a measurement made in July, okay? From Hawaii, the Galactic Center is directly overhead right now. So my collaborators at UCLA are at Mauna Kea right now making the latest, the 2019 measurements for this project. And so what's amazing is from year to year, you can actually see the position of the star move, which is not the case for most stars in the sky. And if you map out in orbit, year after year, you see that this star is moving at incredibly high speeds. So you see this star, SO38. You see SO2, which is on this blue orbit. It has already gone around once and has already gone around a second time. It's kind of like Jupiter gone wrong. When you have a star that close to a black hole, you can actually not only look for Einstein's first order gravitational effects, you can also look for Einstein's second order effects. And so right now, many of the scientists are very excited about this second orbit because it allows them to look for predictions of Einstein's general theory of relativity that have never been seen before. So we want to stay tuned for that. When you map out these orbits and actually do a fairly simple calculation, and I mean that introductory physics students can do this with some support, and we do this in our intro courses. You map out, you can calculate that the amount of mass in that core is 4 million times the mass of the sun in a region that's much smaller than our solar system. So it's absolutely amazing, and there's few physical objects that could explain that density of mass other than a black hole, and most of them have been ruled out. So we think, we're fairly certain that there is a supermassive black hole at the center of our galaxy. The telescopes that made the pictures of M87 are hard at work to make a picture of our galaxy's central black hole, and I'll show you this animation here. And again, each one of these represents a different star. This is the position of Sagittarius A star, the dynamical center of the galaxy where we think the black hole lurks. And the animation is going to go over a function of time. So you'll see the year change here. And you'll notice that the stars toward the center move much faster because they're closer to the mass, which is causing their motion. Okay? And again, this is all based, this is an animation, a cartoon, but it's all based on real observations by the UCLA group. And so you can see that the amazing thing is that some of these stars have managed to go around at least once. Okay, and this animation ended almost 10 years ago, so things have increased since then. All right. Last moment here. What would happen if you observed me fall into a black hole? Warning, don't try this at home, okay? So, well, as you pointed out earlier, one of the first things that would happen is you would start to fall very, very slowly, because if you guys are the observers, in the reference frame that you're observing compared to the reference frame in which I'm located, there's a shift. And so I would appear to, from your perspective, to move more and more slowly because time appears to slow down due to the curvature of space and time, okay? I also would contract, and I would become much, much redder because the light that would be emanating from me gets shifted longward. So if I had optical light coming from me or infrared, it would shift down into the infrared or microwave, okay? And then the effect of that is that you would become redder. You also have tidal forces. You have differential gravitational forces pulling and shredding you. So you would get very, very long and thin, and eventually you would become so stretched out that most of the bonds in your body would be destroyed. It would be incredibly unpleasant. And as this gentleman in the front row said, from your perspective, I would probably hover forever. It would be incredibly unpleasant for you and me because you would just see me there hovering in this shredded spaghetti-like structure. I would have probably crossed over, and there's no information on what that would be like. I can only imagine that you get reduced to atoms and subatomic particles, and it's very, very unpleasant, not able to report back. So I don't recommend you do this, but this is what happens. And I'll just leave you with the idea that you should be staying tuned to the news, because we do have a chance with the Event Horizon Telescope to actually image the shadow of the black hole in our own galaxy. And we predict that it's going to look a lot like M87. Again, this also shows you, this is a sketch showing you the size scale of our solar system, which is here. And this is where Voyager 1 is. One of the Iowa instruments is on that. And you can see that all of that would fit inside the black hole. And that's, for our galaxy, there's 4 million solar masses tied up in that. And so this is just a picture, a sketch of where the Event Horizon telescopes are located, and they're all pointed toward the same object. And all this, you have to have perfect weather at all these sites, which is pretty hard to organize. And then you have to combine the data later. They get very, very accurately time-stamped. You send them all to a central distribution facility, and they get all correlated, and then you begin the hard work of trying to reconstruct these images. But this is coming. I expect that by the end of 2019 or possibly into 2020, we will have an image very much like the one of M87 for our galaxy. So stay tuned, and it will be a very exciting day when that happens. So I'm happy to answer questions that you might have. Thanks so much.
Okay.
Yeah.
John, can you turn on the cordless, please?
Yeah, what did you just say?
I'm talking to the woman across the hall. There we go. We're both pushing the button at the same time.
There we go.
Okay, and the reason you have to talk through the microphone is the people who are watching us live on the internet won't hear your question if you don't ask it in a microphone.
Thanks, that could have been helpful.
Okay, you have to wait. So I heard a piece on the radio with Joel Palca, the science reporter for NPR, about the LSST in Chile, and I didn't really understand it,
Right.
but I think I have a better understanding of it. But it's being built right now.
It is, right.
And so would you be able to use that? Would that help you in your research?
Yeah, that's a great question. So
'Cause
the
can you explain what that
for sure.
LSST
Yeah, so the LSST is one of the major new initiatives that the National Science Foundation is supporting. So this is going to have a component of it, if not the entire thing, a very large component is American astronomy. And LSST stands for Large Synoptic Survey Telescope. So this is it's really interesting you ask about this. This is a very different telescope. The whole goal of the LSST is to scan as much of the sky as you can see from that site many times a night, and to look for, to store all the data in these large data sets, and to look for sources that blink on and off at all different time scales. So there will be a role to study the center of the galaxy, but the purpose of that telescope is actually to get a map of the sky that has a time component.
Right, and I think what he said was that then they would share with the people who are studying that aspect of it, that's what's happening, and so they could.
I think it's going to be it's actually a really, really cool project for people who are interested in computer science and big data to get involved with, because unlike a telescope where you write a proposal, it has to be approved, you go to the telescope, you make the observations, this telescope is going to be releasing its data out into the world all the time. And so you'll be able to get an app on your phone that will alert you when a particular source in the sky, there's going to be thousands of sources of blink. And then you as an astronomer, or even someone in the public, might want to follow up on that source. So it's actually going to be, it's a little overwhelming. There's going to be so much data available that one of the main things that people are doing right now is actually getting organized to figure out what's going to happen when that fire hose of data turns on.
Well, and so there obviously are people there.
Yeah.
But they're not watching the night sky. They're watching
yeah,
the
I mean,
LSST
this will mostly be an automated robotic thing. This will be very different than an observer or a technician. Like right now in Mauna Kea, when my colleagues are there, there's a technician at the telescope. The observers are actually at lower altitude, because at high altitude you can not be clear-headed, and so the astronomers are actually down at about 4,000 feet in the village outside of Mauna Kea. And they can go up and check on things, but they actually want them to do their coherent science observing from low altitude, and they videocon into the observers who are in an oxygenated environment. Because it's like, it's 15,000 feet, so you just don't. A famous story from when I was in graduate school was one of my advisors said that she had her PhD observations set from Mauna Kea, and she got everything organized. She had like 4 hours of time for her dissertation. And in that fog of being up at high altitude, she forgot to take the telescope cover off.
Classic.
And that was it, classic. And so she had to do a different project. And so they're actually, as observatories actually have high altitude doctors on staff to help astronomers make the choices about when they should be up there and when they should be down below. So but you're absolutely right. LSST is going to be a total revolution in astronomy. It's going to be very different. And so we're actually trying to convince, in our department and in the field, we're trying to convince more computer scientists to come and join us, because we're not going to be able to do this with the standard physics and astronomy courses. We need to know how to handle these large data sets. It's going to be very exciting. So,
does it run on C#?
Does it what?
Does it run on one of the programs, C#?
No, the programming language that astronomers tend to use is called Python. So some of you may have heard of Python. If you are thinking about a career in astronomy, take an online course on Python ASAP. It's free. What other questions do you guys have?
Why is I didn't catch the number, but NGOU812 or whatever your favorite galaxy?
Why is it my favorite galaxy? Just purely aesthetics. I think it looks awesome.
Okay, now I have to ask the really basic question. You were showing pictures of these galaxies and their whirls or whatever.
Right.
Why do all the particles make a ring around the equator instead of being out in three-dimensional space?
It's an awesome question, Beth. So it's an amazing question, because if you think about it, think about the shape of our gas. Think about the shape of our galaxy. Think about the shape of our solar system with the sun at the center and galaxy or planets in a disk. Think about Saturn, a big planet with rings. So the answer is, it's very fundamental. When you have a large cloud of gas, as it's rotating, because a lot of things in the universe are rotating around their own axis, as a rotating sphere of gas collapses, the natural shape you get because of angular momentum is a sphere, and then you have a disk of debris. So when our galaxy formed, it formed out of a big cloud of gas. When Saturn formed, it formed out of a smaller cloud of gas in our solar system. When our solar system formed out of a cloud, it has the same shape. So it's not just a coincidence. There's a physical reason behind it.
That's why I was a biology major, not a physics major.
Okay.
If you go back to like when the big boom happened and then looked at all of the debris from all of that and then track to see where it went and what like changes it made, maybe you might be able to find more evidence of what its potential is now.
Yeah, no, that's a good question. So the big boom or the Big Bang is kind of just a name for a time in the universe when things were much more tightly packed and when they were really, really hot. And so the bang there, really what it corresponds to is two things. One, that the physical conditions were so extreme that matter was constantly being created and destroyed. It's really hard for us to even know what that was like. And at some point, we think that soup got a big injection of energy and expanded. It's called inflation period, right? And it cooled down. And at some point, About 300,000 years after that moment was really the first time that we could see light, that atoms were able to remain stable. So in that early, we call it the Dark Ages, in that early part of the universe, atoms weren't even stable enough to let light pass through them. And so a lot of scientists are really interested in this moment. 300,000 years after the Big Bang, there's this moment called the epoch of reionization, when the universe kind of finally turned on. That's the oldest light we know about. And so there's a whole group of scientists trying to observe those original hydrogen atoms at that moment. And it's a really, really tough experiment because that hydrogen light has been shifted to a very low radio frequency. And then you've got the universe is made of hydrogen, so you've got all the other components filling up the universe. So you have to systematically remove each component. So there's many scientists, many graduate students who are solely trying to remove one tiny component of nearby hydrogen to get at the golden nugget of the epoch of reionization hydrogen. So it's a really exciting field, and it's a technically challenging field, and it's a scientifically, it will be a really, really big discovery if we get there. But I would say it's at least 10 years out. But that gets to your question of beyond that, earlier than that, we have no way to observe it. But the earliest time, the epoch of reionization, is when we can start using the techniques that we know with light to observe. So.
Anybody? Oh, there's one more. Oh,
Yep,
there's a couple more.
Okay, good. Yeah.
Is rotation absolute or relative?
What do you mean? You mean like if a cloud is rotating?
Yeah. What's it rotating relative to?
I guess it's rotating relative to a standard of rest in which there's no rotation.
What do you mean by no rotation?
I mean, at some point you would define a coordinate system in which you didn't have any motion. And then if you see motion against that, you would have something called rotation. So it could be either or. You could define a coordinate system in which you are in the rotating cloud, and it could be rest, but then you'd see the other object rotating. So.
Isaac Newton believed in absolute space.
Right.
So does anybody believe in that these days?
Well, I mean, this is the classic shift from Newtonian physics to, general relativistic physics. So I think in our world, we only need Newton. But if you get to these extreme environments, you have to invoke Einstein's revision of Newton's laws. So. But from our perspective, we don't need Einstein. I mean, none of us walk into a black hole. None of us are going to encounter anything relativistic tonight on our walks home. But out there in the maybe. We'll see how exciting people's nights are. So we don't need Einstein right now. But when you start to probe these more extreme things, you do need him. So.
In the giant multi-observatory image you showed earlier, you pointed out a few star clusters.
Yeah.
Do those things shine so brightly in X-rays just because stars shine brightly in X-rays, or is it something special about star
That's a
clusters?
great question. Stars inherently probably don't have a lot of X-ray emission. I mean, we know the sun will have moments where it has a burst and there's X-rays associated with it. The stars I showed that have these sort of X-ray halos around them, those stars are really, really unusual stars that seem to only form in the galactic center. The winds from those stars, when they collide, they can shock gas to X-ray temperatures. So I didn't show this, but what you're actually seeing is kind of a halo around those clusters that is million-degree gas that gives off X-rays. So yeah, you're absolutely right. And a regular old star like the sun would not normally have a lot of X-ray emission associated with it. So.
I feel smarter just being in the room with all you smart people. Okay, one more question, then we're going to let her go.
Good questions tonight.
So what have you gotten to name?
That's a great question, Maeve. I have gotten to name several of those little filaments, so I don't know if I can show you. I've named one the Pelican, which I really like. I like birds. Let's see if we can find the... Unfortunately, I don't think this image has the Pelican on it. No, the Pelican is located right about here. And what's amazing about the Pelican actually looks kind of like this. If this were on its side, could you see how it's like a pelican? This one a little bit. So there's a filament. What's really cool is it almost seems like the magnetic field is turning over and becoming parallel to the plane. And at that point, there's a beautiful little filament that seems to have a beak. And so I named it the Pelican. So.
Well, thank you very much.
You're
This was
welcome.
wonderful.